Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intricate dance of celestial bodies, the precise mapping of the heavens, and the very act of charting a course across vast oceans all owe a significant debt to the mathematical genius of Abu Abd al-Muhammad ibn Muadh al-Jayyani, a scholar of 11th century Islamic Spain. Al-Jayyani's legacy rests, in no small part, on his profound contributions to spherical trigonometry, a branch of mathematics essential for understanding and quantifying the relationships between angles and sides of triangles drawn on the surface of a sphere. His work, a cornerstone for astronomical and navigational endeavors, continues to resonate in our modern world, a testament to the enduring power of his mathematical insights. Al-Jayyani's intellectual journey began with a critical challenge of the need for accurate astronomical calculations. The precise determination of celestial positions, the stars, the planets, and the moon, was paramount for civilization deeply invested in astronomy, both for its scientific value and its practical applications. Accurate astronomical knowledge was vital for determining prayer times, establishing religious calendars, and, of course, for the practical art of navigation, a skill crucial for trade, exploration, and the burgeoning expansion of Islamic influence across the Mediterranean and beyond. The problem, therefore, was how to accurately solve spherical triangles drawn on the curved surface of the celestial sphere. The solution Al-Jayyani presented and refined was the application of the Sine Law to these spherical triangles. This elegant mathematical principle provides a direct relationship between the sines of the angles of a spherical triangle and the sines of the sides opposite those angles. Specifically, the Sine Law states that for any spherical triangle, the ratio of the sine of an angle to the sine of its opposite side is constant for all three angle side pairs. This seemingly simple relationship unlocks the ability to calculate unknown angles or sides given the known values of the other elements of the triangle. Al-Jayyani, through his meticulous work, demonstrated how to apply this law to a variety of astronomical problems, enabling more precise calculations than previously possible. A tangible example of Al-Jayyani's application of the Sine Law lies in his capacity to determine the angular distances between celestial objects. By treating the celestial sphere as, in essence, a giant curved triangle, he could utilize the Sine Law to calculate the distances between stars, planets, and the horizon. This was a significant advancement, allowing astronomers to refine their understanding of the cosmos and navigators to improve their ability to chart courses. The ability to accurately measure celestial distances was, at the time, a critical component of astronomical observation and was also a vital skill for any mariner charting a course across the seas, relying on the stars for guidance. This work on the Sine Law was a foundational piece of Al-Jayyani's broader contributions. It provided the bedrock upon which he built more complex astronomical models and computational techniques. Without a solid understanding of spherical trigonometry, the subsequent advances in astronomical tables and predictive methods would have been impossible. His mastery of this fundamental tool allowed him to delve deeper into the intricacies of celestial mechanics. The enduring relevance of Al-Jayyani's work is strikingly apparent in our modern world. Spherical trigonometry, the very field he advanced, remains a core component of technologies we take for granted. Consider the Global Positioning System, or GPS, which relies on a network of satellites orbiting the Earth. GPS receivers use signals from these satellites to calculate their position. These calculations, at their heart, involve solving spherical triangles. The curvature of the Earth is a fundamental consideration in determining accurate coordinates, and the principles Al-Jayyani helped to refine centuries ago form the basis for these calculations. The same principles are used in satellite navigation systems and in the precise determination of the positions of aircraft, ships, and even smartphones. Al-Jayyani's work, in essence, provides the mathematical framework for understanding and navigating a spherical world. His contribution to spherical trigonometry was not born in a vacuum. He stood upon the shoulders of giants, drawing inspiration and knowledge from earlier scholars. The intellectual landscape of his time was rich with the work of Greek and Indian mathematicians, whose contributions laid the groundwork for his own advancements. Menelaus of Alexandria, a Greek astronomer and mathematician who lived in the 1st century CE, had already laid some of the groundwork in spherical trigonometry. Menelaus's ** introduced the concept of spherical triangles and established fundamental theorems, including Menelaus's theorem, which provides a relationship between the sides of a spherical triangle and their intersections with a great circle. Al-Jayyani was familiar with Menelaus's work and clearly built upon it. He expanded upon Menelaus's foundational work, refining and extending the mathematical tools available to astronomers and navigators. He built upon the legacy of earlier mathematicians, translating and commenting on their works and integrating their knowledge into his own system. The impact of Al-Jayyani's work extended far beyond his own lifetime. His contributions to spherical trigonometry directly influenced the subsequent development of Islamic astronomy. His methods provided a framework for later generations of astronomers to refine their calculations and develop more sophisticated models of the cosmos. The increased accuracy that his methods afforded was a powerful catalyst for advancements in the field. His work provided a critical foundation for the flourishing of astronomical knowledge that characterized the Islamic Golden Age. The advancements in spherical trigonometry, specifically the application of the Sine Law, facilitated the creation of more accurate astronomical tables, the development of more precise methods for predicting celestial events, and the improvement of navigational techniques. His legacy, therefore, is not merely a collection of equations and theorems. It is a testament to the power of mathematics to illuminate the universe and to guide humanity's journey through it. The advancements in spherical trigonometry that Al-Jayyani pioneered proved instrumental in his subsequent work on astronomical tables, a domain where he achieved remarkable precision and efficiency. The central intellectual challenge he confronted was the inherent difficulty in accurately predicting celestial events, from the subtle dance of planets to the dramatic occurrences of eclipses. Existing astronomical tables, while useful, often lack the necessary refinement to meet the demands of increasingly sophisticated observational data. Al-Jayyani's solution lay in a meticulous approach centered on the construction of highly detailed trigonometric tables and the development of computational techniques that leveraged these tables to their fullest potential. His primary objective was to enhance the accuracy of astronomical calculations, specifically those pertaining to the prediction of eclipses and the determination of planetary positions. To achieve this, he embraced and extended the foundational work of earlier astronomers, including Ptolemy, whose asterisk Almagest asterisk served as a pivotal text. Ptolemy's influence is readily apparent in al-Jayyani's systematic approach to astronomical modeling and table construction. He, like Ptolemy, understood the necessity of a robust mathematical framework for representing the cosmos. However, al-Jayyani, armed with the tools of spherical trigonometry, particularly the law of sines and its related theorems, was able to surpass Ptolemy's precision. He refined Ptolemy's methods, creating tables that provided more accurate values for trigonometric functions, particularly sines, cosines, and tangents. These trigonometric tables became the cornerstone of his astronomical calculations. They provided the numerical values necessary for solving the complex spherical triangles that represented the relationships between celestial objects as observed from birth. The process involved a series of intricate steps, starting with the selection of appropriate astronomical parameters, such as the positions of the sun, moon, and planets, as well as the observer's location. These parameters were then fed into a series of equations, utilizing the trigonometric values from his tables to determine the specific characteristics of a celestial event. A tangible example of his work can be found in his calculations of the parameters of solar and lunar eclipses. These calculations were not merely theoretical exercises, they were intended for practical application. He meticulously detailed the method of computation, leaving behind a clear record of his techniques. His approach involved determining the times of the beginning and end of an eclipse, the magnitude of the eclipse, the proportion of the sun or moon obscured, and the path of the eclipse across the sky. The level of accuracy he achieved was a significant improvement over previous methods. For instance, in predicting the timing of an eclipse, al-Jayyani's techniques minimized the error, providing results that were far more consistent with actual observations. His meticulous attention to detail extended beyond the creation of the tables themselves. He also developed specific computational methods to solve astronomical problems. He utilized interpolation techniques, which allowed him to estimate values between those explicitly listed in his tables. This was a crucial skill, as it enabled him to extract precise values from the tables, even when the parameters in question did not directly correspond to an entry. He also employed iterative processes, refining his calculations until he achieved the desired level of accuracy. This iterative approach was particularly useful in solving complex equations, such as those involved in determining planetary positions. The modern relevance of al-Jayyani's work lies in its enduring impact on the development of accurate calendars and navigation techniques. His astronomical tables and the computational methods he devised provided a foundation for more precise calendars. The ability to accurately predict celestial events, such as the solstices, equinoxes, and lunar cycles, was essential for the creation of reliable calendars, which in turn were vital for agricultural planning, religious observances, and the organization of daily life. Furthermore, his methods contributed to advancements in navigation. The precise determination of celestial positions, facilitated by his tables, allowed for more accurate determination of latitude and longitude, which was essential for maritime exploration and trade. The influence of al-Jayyani's work extended to subsequent generations of Islamic astronomers. His methods provided a framework for these scholars to refine their calculations and develop more sophisticated models of the cosmos. His influence is especially visible in the work of al-Khwarizmi, a pivotal figure in the development of algebra and whose contributions to astronomy built upon the foundations laid by earlier mathematicians. Al-Khwarizmi, in his astronomical tables, demonstrated a clear understanding of the utility of trigonometric tables in solving astronomical problems. His work, and that of many others in the Islamic Golden Age, depended heavily on the accuracy and efficiency of the calculations that al-Jayyani's methods made possible. The impact of al-Jayyani's tables was also felt in the development of astronomical instruments, which were increasingly used to observe and measure celestial phenomena. The legacy of al-Jayyani, therefore, is not merely a collection of equations and theorems. It is a testament to the power of mathematics to illuminate the universe. His contributions to spherical trigonometry, combined with his meticulous approach to the construction of astronomical tables, enabled a new level of accuracy in astronomical calculations. His work exemplifies the synergistic relationship between theoretical mathematics and practical application. It not only advanced the understanding of the cosmos, but also provided the tools that enabled others to build upon his achievements. His work, therefore, is a critical link in the chain of scientific progress, demonstrating the enduring value of mathematical precision in the pursuit of knowledge. The precision that al-Jayyani brought to astronomical calculation found its practical counterpart in the design and refinement of astronomical instruments. His work, which underscored the importance of accurate measurement, extended beyond theoretical frameworks into the realm of tangible tools. These instruments, crafted with meticulous attention to detail, served as extensions of the human eye, allowing for more precise observations of the celestial sphere. They were essential for translating the theoretical insights of spherical trigonometry and tabular data into concrete understanding of the cosmos. The astrolabe, a device of ancient lineage, received particular attention from al-Jayyani. It was, in essence, a two-dimensional model of the three-dimensional celestial sphere, a sophisticated calculator of sorts. Its primary function was to determine the time of day, the position of stars, and the altitude of celestial objects, all vital for navigation, determining prayer times, and astrological predictions. Al-Jayyani's contributions lay in the meticulous refinement of this instrument, improving its accuracy and usability. He addressed the inherent challenges of projecting the celestial sphere onto a flat surface, ensuring minimal distortion and maximizing the instrument's practical value. The astrolabe's design, a complex interplay of plates, pointers, and scales, demanded a deep understanding of both geometry and observational astronomy. Al-Jayyani's work on the astrolabe built upon a knowledge of earlier scholars, particularly the Greeks. The influence of Ptolemy, whose asterisk Almagest asterisk provided the theoretical underpinnings for many astronomical instruments, is evident in al-Jayyani's approach. However, al-Jayyani moved beyond mere replication innovating and adapting the existing designs to improve precision and ease of use. He likely studied the work of earlier Islamic scholars who had already made significant advancements in astrolabe construction, such as the Born and Musa brothers, but he appears to have surpassed their achievements. His modifications focused on improving the accuracy of the instrument's scales and the precision of its moving parts. This involved meticulous calibration, ensuring that the instrument accurately reflected the celestial positions and time. The construction of a high-quality astrolabe was a demanding task, requiring skilled craftsmanship and a deep understanding of mathematical principles. Another instrument that benefited from al-Jayyani's expertise was a quadrant, simpler in its construction than the astrolabe. The quadrant was primarily used for measuring the altitude of celestial objects. It consisted of a quarter circle graduated with a scale, along with a sighting device and a plumb line. By aligning the sighting device with a celestial body and noting the point where the plumb line intersected the scale, the observer could determine the object's altitude. Al-Jayyani's contribution to the quadrant involved refinements to its design, optimizing its use and accuracy. He likely investigated the optimal placement of the sights and scales, seeking to minimize errors and maximize the precision of the measurements. Specific examples of his modifications include the improvement of the sighting mechanisms and the graduation of the scale with greater accuracy. The techniques for using these instruments, the astrolabe and the quadrant, were equally refined. Al-Jayyani's work emphasized the importance of proper observation techniques and the careful interpretation of measurements. He would have provided detailed instructions, which would have included guidance on how to align the instruments, how to take accurate readings, and how to account for potential sources of error. He would have also emphasized the importance of correcting for atmospheric refraction, which can affect the apparent altitude of celestial objects. His methods have been passed down to his students and colleagues, ensuring the continuation of precise astronomical practices. The impact of al-Jayyani's instrument designs extended beyond his immediate circle. His improvements to the astrolabe and the quadrant facilitated more accurate astronomical observations and calculations. The astrolabe, in particular, became a ubiquitous tool in the Islamic world and beyond, used by astronomers, navigators, and astrologers alike. The quadrant, due to its simplicity and portability, also saw widespread use. These instruments were instrumental in advancing the understanding of the cosmos, enabling the creation of more accurate astronomical tables and calendars. They also played a vital role in navigation, allowing sailors to determine their position at sea. Al-Jayyani's work on astronomical instruments had a direct influence on the subsequent development of instrumentation within the Islamic world. His designs, which emphasized precision and ease of use, were adopted and adapted by later instrument makers. The influence of his work can be seen in the astrolabes and quadrants produced in subsequent centuries, many of which incorporated the refinements he introduced. These instruments, in turn, contributed to the flourishing of astronomy and mathematics in the Islamic world, fostering a culture of scientific inquiry and technological innovation. The legacy of his instrument design is evident in the continued use of astrolabes and quadrants throughout the medieval period, as well as in the development of more advanced astronomical instruments in later centuries. The dissemination of al-Jayyani's instrument designs was facilitated by several factors. The widespread use of Arabic as the language of scholarship ensured that his work was accessible to a broad audience. His writings, which included detailed instructions for the construction and use of astronomical instruments, were copied and circulated throughout the Islamic world. Furthermore, the patronage of rulers and wealthy individuals supported the production and dissemination of these sophisticated tools. The impact of his work extended beyond the Islamic world, influencing the development of astronomical instruments in Europe during the Renaissance. The rediscovery of classical texts and the exchange of knowledge between cultures facilitated the transmission of al-Jayyani's ideas, contributing to the scientific revolution. His meticulous approach to astronomical observation, combined with his commitment to precision in instrument design, left a lasting mark on the history of science. The evolution of mathematical methods within al-Jayyani's work highlights his dedication to both theoretical rigor and practical application, particularly in addressing the challenges posed by spherical trigonometry. His contributions, deeply rooted in the Hellenistic tradition of mathematical astronomy, represent a significant advancement in the techniques available for solving complex geometrical problems related to celestial navigation and astronomical calculations. Earlier astronomers, such as Ptolemy and Hipparchus, laid the groundwork for trigonometric methodologies. Ptolemy's *omega, for instance, provided a comprehensive framework for calculating the positions of celestial bodies, included detailed tables of chords, which served as the foundation for early trigonometric calculations. Hipparchus, credited with developing the first trigonometric table, established the fundamental principles that al-Jayyani would later refine. He understood the importance of relating angles to their corresponding chord lengths within a circle. Al-Jayyani built upon this foundation, striving for greater efficiency and accuracy in calculations, crucial for the precise predictions required by astronomy and navigation. A central problem that al-Jayyani addressed was the need for a more streamlined approach to solving spherical triangles. These triangles, defined on the surface of a sphere, are fundamental to astronomical calculations, allowing astronomers to determine the positions of stars and planets relative to an observer on Earth. Solving these triangles involves determining the relationships between the sides and angles, which is a complex undertaking. The existing methods, while functional, were often cumbersome and time-consuming. Al-Jayyani's solution involved the development of specific trigonometric identities and computational techniques. He made substantial contributions to the development of the Sine Law, a fundamental tool in spherical trigonometry. The Sine Law establishes a relationship between the sides and angles of a spherical triangle, stating that the ratio of the sine of an angle to the side opposite that angle is constant for all angles in the triangle. This elegant and powerful relationship provided a direct means of solving for unknown angles or sides, given a sufficient number of known parameters. His work also included methods for calculating sines, cosines, and tangents, the core trigonometric functions. These functions are essential for relating angles to the ratios of sides in right-angled triangles, and their accurate computation is crucial for astronomical and navigational calculations. Al-Jayyani's methods, while building on the work of his predecessors, offered improvements in accuracy and efficiency. He refined techniques for constructing trigonometric tables, enabling astronomers to quickly look up the values of these functions for specific angles. These tables were indispensable for practical applications, allowing for rapid calculations of celestial positions. An example of al-Jayyani's practical practical application can be found in his work on the determination of the direction of the asterisk, Qibla asterisk, the direction of prayer for Muslims. Determining the correct asterisk, Qibla asterisk requires solving a spherical triangle where the vertices are the observer's location, Mecca, and the North Pole. Using his trigonometric methods, al-Jayyani provided precise calculations, allowing individuals to accurately determine the asterisk, Qibla asterisk, from any location. This demonstrated the direct application of his mathematical advancements to practical religious practices, highlighting the interconnectedness of science and daily life during this period. The impact of al-Jayyani's trigonometric methods extended beyond the Islamic world. His work was transmitted to Europe, where it significantly influenced the development of trigonometry during the Renaissance. The translation of Arabic texts into Latin introduced European scholars to the advanced mathematical techniques developed in the Islamic world. Mathematicians like Regiomontanus, who translated and studied Arabic texts, were directly influenced by al-Jayyani's contributions. Regiomontanus's asterisk to triangulize on the Modi's asterisk, a comprehensive treatise on trigonometry, drew heavily on the methods and concepts found in Arabic sources, including those of al-Jayyani. This transmission of knowledge played a crucial role in the development of European trigonometry, providing the mathematical tools necessary for advancements in astronomy, navigation, and other scientific fields. The influence of al-Jayyani's work is evident in the evolution of trigonometric tables. His methods for constructing and using these tables provided a foundation for later mathematicians to refine and expand upon. These tables were essential for astronomers, enabling them to quickly and accurately determine the positions of celestial bodies. The advancements in table construction, directly influenced by al-Jayyani's work, led to more precise astronomical calculations. This, in turn, facilitated the development of more accurate astronomical models, contributing to the progress of astronomy. The legacy of al-Jayyani's mathematical methods is enduring. The Sine Law, which he helped to refine, remains a fundamental concept in trigonometry used in countless applications today. The principles and techniques he developed for calculating trigonometric functions continue to be taught and applied in mathematics and related fields. His emphasis on accuracy and efficiency in calculations set a standard for subsequent mathematicians. His work represents a significant contribution to the development of mathematical tools, which were crucial for advancements in astronomy, navigation, and other scientific disciplines. The impact of his work on the scientific revolution is undeniable, as his methods provided the mathematical foundation for many of the discoveries that shaped the modern world. The historical significance of Abu Abd al-Muhammad ibn Muadh al-Jayyani resides not only in his specific mathematical and astronomical achievements, but also in the manner in which he bridged the gap between the intellectual traditions of the East and the burgeoning scientific inquiries of the West. His work represents a pivotal moment in the transmission of knowledge, acting as a conduit through which earlier Greek and Indian mathematical and astronomical insights were refined, consolidated, and made available to later generations. His contributions to spherical trigonometry, particularly his advancements in the application of the Sine Law, provided essential tools for astronomers and navigators. These developments were instrumental in charting celestial movements and facilitating voyages of discovery, fundamentally reshaping our understanding of the cosmos and the world. Al-Jayyani's refinement of the Sine Law stands as a testament to his mathematical prowess. This law, which establishes a relationship between the sides and angles of a triangle, is a cornerstone of trigonometry. His work on this law, demonstrated through his careful calculations and methodological clarity, directly influenced the work of later mathematicians such as Nasir al-Bin al-Tusi. Al-Tusi, in turn, built upon al-Jayyani's foundations, further developing spherical trigonometry and applying it to astronomical problems. Al-Tusi's contributions were subsequently transmitted to Europe, influencing the development of trigonometry during the Renaissance. The enduring presence of the Sine Law in modern mathematics, from surveying and engineering to computer graphics and physics, underscores al-Jayyani's lasting influence. The methods he employed, his emphasis on precision, and his dedication to clarity provided a blueprint for future generations of mathematicians. His contributions extended beyond theoretical mathematics. Al-Jayyani was a practical astronomer, deeply engaged in the construction and use of astronomical instruments. His work on astrolabes, quadrants, and other tools allowed for more accurate observations of celestial bodies. The creation of astronomical tables, which cataloged the positions of stars and planets, was another crucial aspect of his work. These tables were essential for navigation, timekeeping, and calendar calculations. The precision of his tables and the methodologies he developed for their creation directly impacted the accuracy of astronomical predictions. This, in turn, facilitated advancements in fields such as cartography and geography. His instrumental designs and observational techniques, meticulously documented, served as models for subsequent astronomers. These instruments, developed to solve practical problems, expanded the reach of astronomy. Al-Jayyani's influence on the scientific revolution is far-reaching, although often understated. His work, circulating through the Islamic world and eventually reaching Europe, laid the groundwork for many of the scientific advancements of the 16th and 17th centuries. His mathematical and astronomical methods provided the foundational framework for the development of heliocentric models and improved navigational techniques. The availability of accurate astronomical tables derived from his work and that of his contemporaries enabled astronomers such as Nicolaus Copernicus and Johannes Kepler to make more precise observations. These observations, in turn, challenged the prevailing geocentric model of the universe and spurred the development of new theories. His work, therefore, acted as an essential intellectual catalyst, contributing to the paradigm shift that transformed scientific understanding. The impact of al-Jayyani's work on the scientific revolution can be seen through the lens of the transmission of knowledge. His methods, disseminated through translations and scholarly exchanges, were adopted and adapted by European scholars. The translation of Arabic texts into Latin, a key feature of the intellectual landscape of the 12th and 13th centuries, played a critical role. Works by al-Jayyani and those of other Arab mathematicians and astronomers were translated and studied in European universities. These translations provided access to advanced mathematical techniques and astronomical knowledge, which were otherwise unavailable to European scholars. The influence of al-Jayyani's work can be seen in the writings of figures such as Regiomontanus, was asterisk to triangulize Amimodi's asterisk on triangles of all kinds. A seminal work on trigonometry drew heavily on the mathematical traditions of the Islamic world. This transmission of knowledge was not a one-way street. European scholars built upon the foundations provided by al-Jayyani and his contemporaries. This led to the development of new mathematical and astronomical theories. The legacy of al-Jayyani extends beyond his specific contributions. His work serves as a powerful example of the interconnectedness of scientific progress. He demonstrated the importance of building upon previous knowledge. He highlighted the value of rigorous mathematical methods. His dedication to accuracy and clarity and the practical applications of his research have resonated throughout history. His work underscores the significance of cultural exchange in the advancement of science. The intellectual cross-pollination between different cultures, as exemplified by al-Jayyani's work, is a recurring theme in the history of science. It is a testament to the power of collaboration and the enduring human quest for knowledge. In conclusion, al-Jayyani's impact on the history of science and mathematics is profound and multifaceted. His refinement of the Sine Law, his astronomical tables, and his instrumental designs represent significant contributions to their respective fields. His work facilitated the development of more precise astronomical models and contributed to the progress of science. His role in the transmission of knowledge was crucial. His influence on the scientific revolution is undeniable. His legacy is a testament to the power of intellectual curiosity, rigorous methodology, and the enduring value of cross-cultural exchange. Al-Jayyani's work continues to inspire mathematicians and scientists. His contributions remain relevant in the modern era. His lasting impact is a reminder of the importance of building upon the knowledge of the past.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.